Okay, so for this example, we're now going to buck an input voltage of 240 volts when we're connecting a load that requires 220, 221, whatever it takes. Got the same group 1 type transformer, okay, 2 windings on the primary, 2 windings in the secondary with my slash ratings. Now when I'm going to buck, I'm going to go ahead and connect across the full set of windings, okay. Now in this instance, again, I've got everything just series connected. So the first step to solve for a buck is what we call volts per turn. And I can solve volts per turn by simply taking the input voltage and dividing by the turns I divvy it up across. Well, my actual input voltage is 240 volts, and how many turns do I go across? Well, I go across 240 on the primary plus 24 on the secondary. So if I take 240 volts over 264 turns, it's going to set up 0.9 volts per turn. And if I look at the connection diagram for chart 4, my load actually gets connected between H1 and H4. Knowing it's 0.9 volts per turn, well, how many turns do I go across? I go across 120, 240 times 0.9 volts per turn, and I actually get 216, close enough. Okay, so for the following example, I've got a multi-winding or dual winding primary and secondary where I've got slash ratings. I can input 120 or 240 and still induce 12 volts in each winding on the secondary side. I'm going to take 208 volts and I'm going to boost that for a load that requires 230 volts. So in a boost configuration, I'm going to go ahead and connect between H1 and H4 like I typically would on the primary side. Now setting up the configuration I've got between X1 and H4, I've got my additive polarities here with this jumper. Okay. So at the instantaneous value of both these windings are actually going in the same direction, and they simply add. Okay. Now the easy part is if I input 208 volts and these are of equal impedances, well, I'm going to drop 104 volts across each winding. And then it's just a matter of doing turns ratio to solve for what gets dropped across the secondary side. Well, 120 as compared to 12, I've got 10 turns on the primary for each turn on the secondary. Knowing that, fairly simple math, I'm going to drop 10.4 volts across each of these. Now where they're all in series, it's just simply adding them up, right? 104 volts, the amount of turns I go across is proportional to the voltage potential. They're all in series, they're all set up for additive polarity. And what actually gets applied to the load that requires 230 volts. 208 plus 20.4. I think it comes around 228. Close enough. And everyone's happy here.